Hello again. Last time we met, we modeled a synchronous process, a process comprising sub-processes that occur in a specific sequence. We will now learn how to model asynchronous processes, processes comprising sub-processes that are independent of each other and can occur in parallel or in a different sequence every time the system operates. We will look again at the smart card system we are modeling in this section. We can see that the system has two functions in addition to alerting about potential crashes in front of the car: pedestrian in front crash alerting and deviation from lane without indicating. This is a wider view than the one we had when we modeled a synchronous part of the system. There, we focused on a specific scenario in which the braking time before crashing into a vehicle in the front was getting shorter and shorter. Now we want to model the system's operation in a more comprehensive manner. Here is a model of the system's top view, the SD. We call the main process road danger warning. The SD is similar to the SD of the previous model we saw, where we refined a synchronous process. As we have just seen, the main process can be modeled as being comprised of three independent sub-processes. But before we do that, we will ask Hopcat to provide us with a definition.
An asynchronous process is a process whose sub-processes do not have a predefined fixed order.
Thanks, Hopcat. Now we will refine the main process. However, while previously we did this by inzooming, which determines process execution order and is therefore fit for synchronous processes, we will now do this by unfolding. A new OPD labeled SD1 is created. We will add to it the three sub-processes we talked about earlier: vehicle in front crash alerting, pedestrian in front crash alerting, and lane deviation alerting. How should we connect these sub-processes to the main process? Using a structural link, of course. There are two types of structural links we can use when connecting asynchronous processes: aggregation participation, which we've already seen, and generalization specialization, which we will learn about now. Generalization specialization expresses a relationship between a general thing and its specialization, or in other words, between a type and its subtypes. For example, car is a specialization of vehicle, and truck is another specialization of vehicle. So what relation should we use here? Aggregation participation or generalization specialization? Are the sub-processes part of the main process or specializations of it? In this system, each sub-process is a specialization, a type of alert from dangers on the road. Therefore, we will use a generalization specialization link. The OPL sentence reads: vehicle in front crash alerting, pedestrian in front crash alerting, and lane deviation alerting are road danger warning. Good! This shows us that the link we chose expresses what we wish to model. Now we must confirm that each sub-process transforms an object. Let's go process by process. The first sub-process deals with something we are already familiar with: warning about crashing into another vehicle. We will model this by adding an informatical object called vehicle in front representation with two states: not yet detected and crash alert. The process transforms the object by changing its states. The second sub-process executes a transformation similar to that of the first one, this time for the representation of pedestrians. We will therefore add an informatical object called pedestrian in front representation with two states: detected and run over alert. Again, the process is what causes the state transition. Regarding the third subprocess deviating from the lane, we will add lane set representation with two states, not detected and deviation alert, with a state transition carried out by the corresponding subprocess lane deviation alerting. Let's review what we modeled by inspecting the OPL sentences created. Vehicle in front crash alerting changes vehicle in front representation from not detected to crash alert. Pedestrian in front crash alerting changes pedestrian in front representation from not detected to run over alert. Lane deviation alerting changes lane set representation from not detected to deviation alert. Now every subprocess transforms an object. What about environmental transformees? To achieve the benefit of the system, reducing the probability of crash, the system creates representations of environmental objects, vehicle in front, pedestrian in front, and lane set. We will add pedestrian to SD1 and connect it to the appropriate subprocess with an agent link. Let us add this object also to SD and connect it to the main process with an agent link. Finally, the subprocess lane set warning is made possible only when driving on a road with clearly marked traffic lanes. We will model this in both SD and SD1. What about various representations we modeled in SD1? If we include all of them in SD, it will become cluttered with too many objects and crisscrossing links, which will render SD incomprehensible. So instead, we will create in SD1 a new object called road danger representations. Since each one of the three representations is a specialization of a road danger, we connect it to the three objects with a generalization specialization link. Only this more abstract general object, road danger representation, will be added to SD and connected to Mobileye system with an exhibition characterization link. Additionally, we will connect it to the main process with an effect link. We learned how to model asynchronous processes at the first detail level. You are now one step closer to being able to model a system that will be recognized as an ISO standard, which is what your CEO asked. Next time we meet, you will learn how to refine objects. I'll see you soon.